Good morning, everyone. Welcome to the Quiz AI Talks seminar series, weekly seminar series. Today we have Mr. Ziad El Sayed from University College London. Let me briefly introduce him. He's got his Bachelor of Science in Computer Science and Applied Mathematics from New York University, Abu Dhabi in 2024. And then he pursued his graduate studies in Master of Science in Machine Learning at University College London. And today he's gonna talk about his talk's title is OMem, Dynamic Hybrid Retrieval for Long-Term Memory in LLM-Based Agentic Systems. As you can understand from the title, it's a very hot topic nowadays. Yeah, he recently completed his master's degree, as I said, and now he's working in industry in applied machine learning, generative AI. He's particularly interested in the fields of LLM-based multi-agent systems, AI safety, human-centered AI, and geometric deep learning. And yeah, we're very happy to host today Mr. El Sayed. And it's your time.
Thank you for the very warm introduction. It really is an honor to be here. And without further ado, I'll get started on my presentation. So I hope my screen sharing is fine.
It is fine, yeah.
Awesome. All right. So yes, just to reiterate, the title is OMem, Dynamic Hybrid Retrieval for Long-Term Memory in LLM-Based Agentic.
We can't see the screen now. At this, I can't see the screen now.
Okay, I think that's because I made it full screen.
Yeah.
Is it all right now?
Now it's all right, yeah.
All right, perfect. So yes, the title is OMem, Dynamic Hybrid Retrieval for Long-Term Memory in LLM-Based Agentic Systems. This was done at University College London, UCL, for my dissertation. And it was supervised by Dr. Omer here and by a UCL faculty member, Dr. Philip Treleaven. So yes, it's once again an honor to be here, and I'm really excited to present my research. I hope it's of value. So just a quick outline. I'll start by an introduction and kind of defining the problem, and then just some background and literature review on what's been done in terms of LLM-based agentic memory, our methodology that we use, evaluation, so the data sets that we use and how and what metrics we use to quantify how well our method works. We present our results, and then we conclude and kind of present some ideas for future research. So chapter 1, the introduction. So LLMs are powerful, as we all know, but they do have a limitation of having a lack of persistent memory sessions. So if you've ever used like ChatGPT or Claude and it just forgot something that you mentioned before and you had to kind of remind it, that's kind of the problem that we are trying to solve. And it is a hot topic right now. A lot of people are trying to solve the problem. One of the proposed kind of solutions that large AI labs are doing is to extend the context window of LLMs. But we posit here that this isn't necessarily a solution. It might fix certain things, but ultimately it's about what you retrieve and not just having just everything in your context window. So yeah, so even with larger context windows, agentic settings suffer from context fragmentation over long interactions, and loss of goals and state and temporal coherence. So they kind of become brittle when dealing with temporal information. and then the kind of relevance starts to degrade as earlier facts that you shared are being retrieved. So, of course, on the path to artificial general intelligence, we need agentic LLMs to be able to recall facts, to have a sustained internal state, to track goals and also contradictions over time. So, if you say something and then kind of contradict it later on or say this is no longer valid, it shouldn't kind of bring in memories from the past and see that as an absolute truth. So it should be able to kind of have a time scale and within this time scale be able to contradict previous sort of things that were shared. So just a quick fun visual. For instance, here you're with an celiac, for context, is disease where you cannot have gluten. It damages your cells. So in here we have this figure of an LLM without persistent memory. So in one session you say, I have celiac disease. What are some fun, delicious breakfast ideas? It understands that you have celiac disease, and it says, here are some fun gluten-free breakfast ideas that are safe for celiac, etc. And then you go and ask it the same question without giving it the celiac context in session 2. You say, what is a fun, delicious breakfast idea? And it says breakfast burritos wrapped in a tortilla. So it forgets that you have celiac disease, and it forgets about the whole gluten-free requirement. So this is kind of what we don't want to happen. And then in this case, it's what we are trying to solve, and what our aim is that it'll remember that long time ago the user shared that they have celiac disease. So within this suggestion that I give, I must make sure to I must make sure that it's a safe suggestion. And so you can see here the difference is that in session 2 it says wrapped in a gluten-free tortilla. So of course this can be scaled to several different problems, as you can imagine, over many different fields: healthcare, education, finance, etc. Common memory approaches break down over long horizon reasoning. That's one of our motivations. So just having buffers, for instance, doesn't perform as well. And then you kind of have two camps of retrieval that are done. There's the dense retrieval and then there's sparse retrieval, and each have their own flaws. And yeah, just remember the ultimate goal is to have an LLM remember things that you said earlier in a conversation. So simple dense retrieval based on the conversation history can miss exact like lexical matches. So if I say Anne likes to eat apples, and it might struggle to if I said what fruit does Anne like to eat, it might struggle because you didn't say the word apples. So um that's one flaw with dense retrieval, and then sparse retrieval misses paraphrases. And then hybrid retrieval kind of mixes the two, and you're able to quantify and control how much each contributes. And it isn't explored as much. So what we do in our study is that we explore it, and we do ablation studies to see how much each kind of component contributes. So we say the central claim in our study is that memory should be treated as a first-class configurable subsystem to fit different agent workloads and constraints. So it shouldn't be treated as an afterthought. This is actually parts and parcel of our kind of agentic architecture. So our research objectives are to design a hybrid memory retrieval architecture, integrating those previous components that I spoke about. So like the dense semantic embeddings, sparse retrieval, reciprocal rank fusion, which controls the balance between the two, and then cross-encoder reranking. And we will go on to define each of these a bit more in depth in the next section. But our second research objective is to develop an evaluation protocol with ablation studies. So what happens when we turn on dense embeddings but turn off sparse retrieval, or what happens when we don't do cross-encoder reranking. How much really does each component contribute? And ultimately, our third objective is to be able to benchmark our method on two selected long-term memory datasets, LoCoMo and LongMemEval. So LoCoMo is long-term conversational memory, and we'll go more in depth about each of these datasets and what the task is and how we approach it. So yeah, it's divided into chapters, and the next chapter is background and literature review, where I will just quickly give background on LLMs, agents, agentic AI, memory, retrieval augmented generation. And then the next chapter will dive into the methodology. So as I said, we'll go more in depth on what dense and sparse representations are, reciprocal rank fusion, and cross-encoder re-ranking. And then chapter 4 will be how we designed OMem, including like the ablation configurations. Chapter 5, we go in depth about LoCoMo and LongMemEval, the two datasets that we use, and then what metrics we use to quantify how well our model is performing, and also how we fine-tuned our model and what the environment was so that the results are reproducible. Chapter 6 is results. So just how the model performed generally on the metrics that we defined in the previous chapter. And then chapter 7 will just be a quick conclusion and ideas for future work. So without further ado, we go to chapter 2, the background and literature review. I'm sure all of you are familiar with LLMs. They've sort of taken the world by storm. And what they do is that they learn token level conditional probabilities over sequences so that they take in their objective is taking in a set of tokens and predicting what comes after it, right? And then when you scale this to large quantities of data, it yields strong generation, and as we've seen, it's very capable. But one flaw is that within this formal objective of just a chain rule of predicting the next token, there is no idea of persistence or memory. And so we need to augment LLMs with memory so that they can perform well in long horizon settings. So as we alluded to earlier, context window scaling is not sufficient or efficient for long horizon memory. So expanding a context window becomes a sort of a needle in a haystack situation, where you're gonna have to find the right thing in like a large quantity of data. That's not necessarily, it's not, the solution isn't necessarily always to expand context windows, because it doesn't necessarily make retrieval any better. It just allows you to fit more things in. So we do still need smart kind of retrieval. Long contexts can be expensive, they degrade over length, and as I mentioned, they cannot selectively prioritize content. So practically what this means for us is that on the long term, when we look a few years down the line, if we want AI to be augmented with memory, this depends on external sort of memory subsystems, algorithmic subsystems that know how to retrieve. And then just a quick word on agentic LLMs, a buzzword currently in the AI world. As you've probably seen, everything is now agentic. And all it really means is that our conditional probability model is augmented with planning, tool use, and iterative feedback. So this isn't just an LLM anymore. It's an LLM that can, for instance, go and calculate things for you using a calculator tool, or use web search so that it can find relevant information for you. So there's just like one of the common patterns is that it observes, it plans, and then it acts, and then it reflects, and then it updates its state based on that. And you can imagine this is quite useful for tutoring, healthcare, finance, productivity, etc. So we represent an agentic LLM as a tuple, where f of theta is the base, just the LLM language model. Pi of theta is a policy over actions conditioned on the input and also on the memory. M is a memory store. U is the memory update find action space, possible set of possible actions that the model can take. And so the way this works is that at a time step t, the agent processes all of the input that you've given it and the memories up to that point. It selects an action based on the policy, and the policy is based on the input and the memories. And it executes it, and then after this, it updates the memory. So we have an mt plus 1, which is just the output of the update function. So the important components of memory are continuity. So model should be able to understand a user's goals, preferences, constraints, and past decisions across sessions. Another thing is temporal coherence. So it should have an idea of time and what came after certain things. So if there are contradictions over time, like if I said James likes to eat apples, and then an hour later, after a lot of text, I say, on second thought, James does not like to eat apples, it should be able to handle those contradictions. And of course, if that sentence of James likes to eat apples is just a part of a huge like conversation space, it should be able to find exactly that. So exactly what's relevant when I ask it a question. So yeah, long context is not memory. So a longer prompt is a longer scroll of tokens. So it's not structured, and effective memory really is a dedicated subsystem that can write, retrieve, and reason over accumulated knowledge. So without this persistent memory, agents become brittle, forgetful, and simply reactive. And then in designing memory systems, we've kind of divided it into 4 components. One is granularity, so just how much or at which level of abstraction does it retrieve. So you have raw episodes, which is just the raw text that you're communicating with the language model. You have summaries, so summaries of those interactions, extracted facts. So you'll see that some of the memory systems use an LLM to extract facts, and those facts become memories. And then another thing that is done in the memory literature is extracting entities and like relationships between these entities that then become graphs. So if you just say like James went with Anne to the park, it kind of will extract James and Anne, and then it'll make a link between them, and then maybe likes to go to the park or went to the park. So you sort of, when you start to design a memory system, that's one of the choices that you make. What level of abstraction do I want to encode my information in? The next one is representation. So how am I really embedding our information? How do I quantify how close certain information is to my query? So one way is to do it with dense vectors. The other is using sparse features, and then some people use graphs as well. And then once you've represented your memories, how do you retrieve them? And then just as a response to the whatever representation you've used, this could be semantic similarity, keyword matching, fusion, and reranking, all of which we actually implement ourselves here. And I guess what's really at the crux of this project is having an idea of how much each of these contributes. So is semantic similarity the most important thing, or is it keyword matching? And how much does hybrid fusion and re-ranking contribute? And then you also want some like a management layer. So how am I, for instance, dealing with contradictions? When a contradiction happens, do I sort of invalidate previous memories? What about updates? What if I just add more information to a memory that was already there? And also, you want to control redundancy, so you don't want your memories to become too redundant, and they should make sense temporally. So, like they shouldn't. The timeline should add up. So there should be some idea of a temporal scale. And one other word you might be hearing within the AI world is RAG, Retrieval Augmented Generation. And all that is really is augmenting a large language model with relevant bits of external information um, that can help it answer a query. So it is non-parametric, and it retrieves relevant passages, and they're conditioned on the condition the generator on the query that's given, which is natural, but also on the retrieved context. So if we apply this to our context of conversational memory, our corpus, like the main source of what we augment our large language model with is a dynamic interaction history between a user and an agent, or between several different people, rather than documents. In other words, um, typical RAG is done with like a company, for instance, that has a large set of internal documents that they want to query. Whereas in our context of conversational memory, it's not so much that as much as it's just an interaction history. So, what can an LLM remember about you from a conversation that you've given it access to? And yeah, so if you see our figure, the query comes in, it's embedded. That goes to the retrieval algorithm, but what also goes to the retrieval algorithm is embedded information that is chunked from documents and retrieved. So it goes into the retrieval algorithm. Based on the query, you retrieve chunks from the document, and then what you pass to the LLM is just the retrieved chunks and the user query, and that is like the typical RAG pipeline. And yeah, memory modules are viewed as just specialized RAG systems over evolving stores. So they're not the corpus that we use RAG on isn't fixed here. It is constantly evolving. And in this case, temporal consistency matters. Updates and contradictions are expected. And it should have exact lexical recall, and also be able to kind of understand paraphrasing. So now I'll just very quickly summarize three studies that at the time of conducting my dissertation were at the kind of forefront of this agentic memory research. The first is called OMem, and it uses a graph to create memory nodes that are inspired by the Zettelkasten method, which is a method that people use to study, I believe. So you go through your notes and you create you take the raw kind of sentence, you create like a summary of it, you link notes together. That's what the Zettelkasten method is traditionally, but what they've done is they've gone and implemented this for LLMs for long-term memory. So the representation of a memory is this tuple here, which contains the raw content, a description generated by an LLM, an embedding, a dense embedding specifically, keywords generated by an LLM. If it says like John likes to eat apples, it'll be food, maybe preferences. And there are links to prior notes that are created so that it then becomes a graph. So an extraction function is used to generate the description and the keywords. Specifically, an LLM is used, and ET is computed by just a dense embedding model. And then what it does is it creates links between these nodes using cosine similarity over the embeddings, and also on the description compatibility. So the description generated by the LLM, how compatible are, for instance, two memories together with given these descriptions. And then you have the parameter alpha and the parameter beta that control the strength of each of these sources. And Yeah, the way that you retrieve in this case is you find the dense top k neighbors, but then you also expand it one layer with the immediate neighbors of in the graph. So that was AMEM. There's also ZEP, which has a three-tier hierarchy. So it just takes raw like episodes, which is just like the raw data, the raw like textual data, and then it has like one layer of abstraction above that, which is entities. So who is mentioned and what is being referred to in these episodes, and then above the layer of entities, how do these entities kind of connect together to form communities. And there's a figure in two slides that kind of explains this better. And yeah, so it uh, it it creates edges between between different facts, and these edges have the time created, the time it expired, and the time valid, and the time that it's invalid. So it does take contradictions into account to preserve kind of history and so that it's temporal. So retrieval for us is a function, chi of rho of phi of alpha, where phi searches, rho reranks, and chi serializes retrieved context. And the search in this case uses dense embedding, similarity in the sparse BM25 style keyword search, and also graph traversal. And it has an option for ranking so that you can fuse these different components and also cross encoding. And this is the figure that explains the architecture of ZEP. So as you can see, on the lower level, you have episodes. Above that, you have entities extracted from these episodes. And above these, you can see that different several entities connect together to form communities. And between all of these, there are edges. And fact edges have the four timestamps: the time valid, time invalid, and also the time that it was created and the time that it expired, that it no longer was relevant or truthful. The third architecture the third sort of memory system that we'll talk about is called memo. So there are two phases within memo. There's extraction and update. And what it does is it ingests a pair of messages and it builds a prompt using a global summary of the previous messages, and then a recency buffer that you set of the last M turns and the current exchange. So the current message and the one before it. And then an LLM extraction function sort of gives out the candidate memory facts, so a set omega of memories. And the update phase then decides by comparing each extracted fact to the existing store to do one of four operations. So to add it, to update a previous memory, to delete a previous memory, or to do nothing, so no operation. And then they have another method called memo graph, memo G, which just extends the store into a graph. And here nodes become entities and with embeddings and temporal metadata, and then the edges are the relationships between those entities. And then in this case, conflict handling marks outdated relations as obsolete rather than deleting them. So in the case of the base memo, we have dense top case similarity search. And MemoG adds entity-centric neighborhood exploration and triplet-style matching, so it traverses the graph and kind of retrieves based on what it finds. So that was background and related work. Now we go on to our methodology. So for us, we position memory retrieval as a ranking problem. So the memory store is a set of memory items. The query is the current user request or a subtask queue created by the agent. And the ultimate goal is to return a small ordered set of the most useful items for solving the current step. And the key constraint is that K must stay small. So we have a prompt budget or latency budget. So it's a function of both the recall, but also the ranking quality. So how much with latency and does it go over the prompt budget? So we have two failure modes that motivate hybrid retrieval. We have lexical specificity that dense retrieval can miss. So this is just finding exact names, numbers, IDs, dates. And then you have the semantic paraphrase that sparse retrieval can miss. So just things that are synonyms, things that are conceptually similar. Sparse retrieval tends to miss this if the tokens don't overlap enough. And the methodological response in our research is to use both of them and then fuse them and re-rank them, and also importantly to see how much each of them contributes. So we might find that really dense retrieval is vastly more important than sparse retrieval. Dense retrieval entails each memory item is mapped to an embedding vector, and the query is also embedded in the same space. And then you perform a cosine similarity scoring to see how semantically similar the query and the memories are. And then you find the top K nearest neighbors using cosine similarity, and that is your candidate set from the dense retrieval. Memory items can be terms, summaries, extracted facts, or just chunks of information. Exact search is expensive, as you can imagine, for a large N. And approximate nearest neighbor indices trade a small recall drop for large speedups. So it's robust to paraphrasing because it kind of relies on this embedding space wherein concepts that are close to each other rank similarly, have similar values. But its weakness is that, on the other hand, it can underweight rare tokens and exact match details. So these are things like nouns, like names, for instance. It doesn't, on paper, just theoretically doesn't perform as well. On the other hand, we have the sparse retrieval to complement the dense retrieval, and what we use is BM25 retrieval specifically, which is a classic information retrieval ranking function. The input to this function is a query, which is your question, and a collection of documents, or in our case, memories. And what it outputs is a relevance score for each memory. And then, just like the dense retrieval, it returns the top K most relevant memories based on the ranking function. And the intuition behind the BM25 formula is that it rewards a memory if it contains query terms, especially if they're rare terms. But at the same time, if a term is repeated many times, it doesn't sort of always have the same effect. There's diminishing returns on that. And then long memories are also normalized. So there's a length penalty so that they don't just win by being long. You can imagine if a memory just is infinitely long, it'll contain pretty much everything, right? And so it it doesn't it shouldn't work that way. It shouldn't There should be like a length penalty um so that longer memories don't win by just the virtue of them being long. They should actually be relevant. As I've shared, the strengths here are that it finds exact matches, so dates, names, IDs, and the weaknesses is that it struggles with paraphrases and synonyms. Our next component is the reciprocal rank fusion, and you might ask, why do we use fusion instead of just using like a single weighted score? And the reason is that dense and sparse scores, they operate on different scales and different distributions, so you can't mix them with a weighted sum. Or it might be quite difficult to do so, rather. But in the case of rank fusion, it kind of just keeps the best of both. So if you notice with the formula, here it operates over the dense and sparse results, and what it does is there's 𝐀𝐤, which is a stabilizing constant, so that it's like a damping constant, so that it doesn't diminish too quickly based on the rank, and then it just takes the ranking of each list, so it kind of just combines the top set results from each list, the dense list and the sparse list. So you can think of it as a way to fuse two lists based on the best results from both. And some of the choices that we make are the depth of the fusion. So larger candidate pools improve recall, but that comes with latency cost. And the benefits of fusion is that it captures both, like the paraphrasing aspect of the sparse retrieval and of the dense retrieval, and the exact match signals aspect of the sparse retrieval. And then kind of the last layer, or the last component, is reranking using a cross-encoder. So reranking using cross-encoder scores a query and the memory jointly. So that is that can capture interactions that your standard bi-encoder embedding might miss. But the caveat with this is that it is expensive to use. So what you want to do is to keep the candidate set small. So when you pass from reciprocal rank fusion to cross-encoder re-ranking, you want to set a reasonable top n number, and you re-rank only that short list. And then since this was our last layer, what comes out of the cross-encoder re-ranking goes straight to the prompt, straight to the LLM. So the methodological goal of the cross-encoder re-ranking is to kind of push this expensive computation to a stage where it buys the most quality for us. So we make sure to pass to it only refined, like a good set of a good candidate set. And then, as you can imagine, there's like a consistent format for how these memories are ranked and how they are passed to an LLM based on kind of a pre-written prompt. And the prompt typically contains like system instructions. So for instance, don't be too verbose or talkative. Respond only to queries that you have information for based on the memories we augment you with, etc. And of course, the prompt also contains the memories that are retrieved. So kind of the whole point of our system. And I think it's clear. So just a summary is that first we do dense retrieval, then we do sparse retrieval. We combine the two with retrieval reciprocal rank fusion. And then as a final layer, we do cross-encoder re-ranking and assemble them into a prompt that can then be used for the generator. And the goal of this really is that within our system, it's entirely modular, so you can enable or disable each component, and you can set them to be to contribute more or to contribute less, as we'll see in the next section in the results. By default, it does hybrid retrieval, but you can just toggle that off. The latency won't be anything too crazy, so it's actually usable in real time. And it's reproducible, so yeah, we set seeds so that it's always kind of the same, and so that it's a fair comparison with other methods. And it is usable as a drop-in memory, so you can use APIs to kind of to test OMem on. So it isn't a fully symbolic world model or planner. Really what it does is explore how memory is represented, searched, fused, packaged, and how each of these components contributes. Yeah, so the schema for a memory item is a content text. So what really to retrieve, which memory to retrieve, metadata, which is like when this was, what, like timestamps and source turn and memory type. So if you have like a long list of interactions between a user and an agent, the time matters. So just timestamp for when each message was sent. And also source turn, as in like, is this a message sent by the agent or is it a message sent by the user? Or if it's a conversation between 20 people, who is speaking for each at each turn. And of course, the dense embedding vector and the sparse representation. So this the idea is that the store grows larger as the agent interacts with the user. Yeah, so of course, when we do dense and sparse indexing, we link them back using a memory ID. Each memory has an ID, so that we can just then link them back to the memories, and they share the IDs. Right. So yeah, I think this was covered, so that's fine. Yeah.
Can I
Just
just
being
add, it's going very well, but if the Quiz AI team or the other participants have any questions so far?
Yes, absolutely. Please.
If yes, because I see some people in the Quiz AI Center, and if you have any questions, please interrupt us. Otherwise, I think we're fine to go. We can continue, I believe.
Yes, absolutely. Feel free to interrupt at any point. And yeah, thank you, Dr. Omar. Yeah, so I'll just move on if no one has any questions. And we'll have a Q&A at the end as well if if you come up with any questions as it goes. But yeah, do feel free to interrupt at any point. Just turn the mic on and ask a question. That's fine. That's completely okay. All right, so if no one has any questions, I will just move on. So I do think I'll just be conscious of time, and I do think the point has come across on kind of what the different components are. And this is just like a quick pseudocode representation of the whole method, really. Keeping in mind that each component is can be turned on or off. So now we move on to how we evaluate our method. We evaluate it on two data sets. So LoCoMo and LongMemEval, and LoCoMo stands for long-term conversational memory. And what these two data sets are just very long chats between different people and also between users and agents. And they were generated, for instance, in LoCoMo's case, it was generated using an LLM, giving different people different roles. And the reason why we used two benchmarks is because we didn't want to overfit to kind of one of the data sets, so that we don't learn one of the data sets quirks, really, so that it just generalizes and just like sort of as a proof of concept that it works in multiple different domains. Right, so the dataset structure is around 9,000 tokens per conversation and 300 dialogue turns. And the conversations are between two virtual agents. Each has like a certain persona and has a temporal graph based on what the timestamps are. As I mentioned, the dialogues are generated by an LLM, but then refined by humans. So there are three tasks within the larger LoCoMo dataset. There's question answering, event summarization, and multimodal dialogue generation. We use the QA question answering task. So generate an answer based on a question and a history of utterances. So there are 5 question categories for the LoCoMo data set. There's single hop, so if you can recall a fact from one session. Multi-hop, so using different sessions, like the example of the earlier example of the celiac disease and the gluten-free, that's a multi-hop question. Temporal, so if I say what happened the day before Jane went to the park, it should be able to kind of see which date that happened and then go a level before that or a day before that and see really what happened. Open domain, so just external knowledge requests. Like for instance, if you ask it what NASA is, that doesn't really have anything to do with the memories. It's just based on its internal knowledge representations. And then adversarial questions that it really shouldn't answer. So it's sort of like trick questions or gotcha questions that kind of try to lure the model to respond, but that it doesn't have sufficient information for. So yeah, just very quickly, these are some of the questions. So for the single hop reasoning, it's like last night we celebrated my daughter's birthday. The question would be whose birthday did X celebrate? It would say daughter. And yeah, it just translates to the different categories as I described them. And then you have the LongMemEval data set, which is quite longer, and I think this data set emphasizes the needle in a haystack situation, where you have just so much text, and the question will be about just a small piece of that text, and it's supposed to be able to retrieve that small component from this larger data set. So 30 to 40 sessions per history and about 115,000 tokens on average. And we use the LongMemEval S for small. There is a larger version of this data set. And similar to the previous like single hop, multi-hop categories, we have temporal reasoning, knowledge update, personalization and preference. That's a new one, so it should learn about a user's preferences just based on things they've said. And then just consistency checks over single sessions. So even when you don't have these dependencies between sessions, the model must maintain its coherence. Right, so each data point contains like sessions and then a question and a golden answer. And we use 3 tokens. We use F1 and blue1, which measure the sparse kind of lexical overlap. So in a nutshell, it's just how many of the same words appear in the golden answer and in the answer that the LLM says. And then LLM as a judge, which you might be familiar with. It's a metric where you basically ask an LLM, hey, here is the golden answer. This was the question, and this is the answer given by my LLM. Is it a correct answer? And LLM as a judge appears to be kind of the standard metric in these like memory tools. Right. So yeah, so it can handle temporal answers where format can differ. So like blue and F1 don't sort of score differently for 7 May versus May 7th, but an LLM knows the difference. And there are different prompts, as I mentioned, for LoCoMo and LongMemEval, where we just emphasize different things in accordance with like what the previous state of the art did. And important hyperparameters are the number of memories passed ultimately to the generator, what the shortlist is for the cross-encoder reranking, the damping constant for reciprocal rank fusion, so that like constant that we had in the denominator that controlled the effect of the size, and sparse retrieval toggle so that you can turn it on and off at any point. And the results are as follows. So the previous state of the art on the LoCoMo dataset was Memo, and we evaluated on GPT-4o Mini, so the same model evaluated in Memo, and we achieve superior results. And with 4o, we achieve even better results across all sort of 3 metrics. This is how it performs per category, so it does perform better across the board. And particular gains in like categories like the single hop And yeah, it performs better for each category on the F1 score. The same with like LLM as a judge metric. And you can see that it performs really well on the temporal reasoning as well. And I guess what we learned from this is that because we saw how Memo was structured, and it was like a graph-based architecture, and it involved using conversation turns, etc., that sometimes simple, just dense and sparse embeddings might be sufficient on these benchmarks. And we see that the latency is reasonable, so it is within like a time frame that a user can interact with a model. And then we just combine the effects or compare the effects of sparse retrieval. So the lambda sparse controls to what extent we rely on the sparse embeddings, the sparse representations, and you see that it in this case actually turning sparse off, so having 0 for lambda sparse performs the best. So that is an insight in and of itself. In this case, for this data set, sparse embeddings, although we expected them to matter, they didn't really. And this was the best case here was when lambda sparse was 0, so when it was just dense embeddings. And then we tightened the budget. So you notice here top K is 50 and cross-entropy cross-encoder candidates is 100, but here we have 30 and 50, so the budget is tighter. And we see some gains at 0.2 for sparse. So here, when you had less candidates, sparse encoding actually did give us like a bit of a gain. So that's also just another insight from our research. And then here are the ablation studies that we did. So we have dense cross-entropy, sparse cross-entropy, hybrid, so the combination of both with reciprocal rank fusion, and then that plus cross-entropy, plus cross-encoder, sorry. And we see that dense plus cross-encoder performed the best. So in this case, the sparse underperformed. And it's just like the same for the F1 score and the LLM as a judge score. And then we move on to the LongMemEval dataset, and we compare to like the previous state of the art, which was ZEP. And across like 4.0 mini and 4.0, we perform better at a reasonable latency, so it's still within like a reasonable time frame. And these were the different categories, and OMem performs better across the board except for the single session preference. ZEP outdoes OMem in that case, but for the rest, we kind of achieve superior results. And yeah, that was on GPT 4.0, and it's the same kind of for GPT 4.0 mini. We noticed that like the single the preference isn't learned that well in this case. ZEP, the way they've structured their algorithm, it works better with preferences. So that was one thing where our model underperformed, but it did perform better on all the other categories and just overall. And we sort of do the same study with the turning sparse off and kind of changing its strength. And we notice here in this case when we have like a larger budget that at 0.5, so somewhere in the midpoint, it performs the best. So here's the sparse signals are kind of contributing. So 10 questions that it gets correct over when you turn sparse off. And then when you have like a tighter budget, the result is the same. So 0.5. So having like an equal balance between dense and sparse embeddings is key in this data set in this case. And then just very quickly, we have the ablations, so the accuracy per category. And we just move on very quickly to conclusions. So OMem achieves strong results on both the benchmarks. It improves over the state of the art with competitive latency. Dense retrieval is consistently like the strongest single component. And in both cases, we know as that sparse only retrieval was the weakest kind of ablation done. And reranking does help on LoCoMo, but it was not beneficial in the case of LongMemEval. So yeah, as I said, like in LoCoMo, cross-encoder reranking improved the overall scores. The hybrid fusion was competitive. It didn't perform poorly, but the dense configurations dominated in this case. And then in the case of LongMemEval, dense only performs the best. And in fact, depending on the category, a cross-encoder and fusion can degrade the performance. Our limitations are that evaluation focuses just on the text-based question answering, so it doesn't really fully capture the tool use or planning, like the whole agentic aspect of things. It really stress tests the text-based memory. And we don't learn the parameters. So dense and sparse encoders are fixed. They're not adapted. And then future work directions are multimodal memory. So just like testing on images, for instance, or audio. Multi-agent memory, so like managing memories between several different agents. We work on single agent memory. Using like more realistic real world benchmarks. And adaptive retrieval, so just tuning retrieval and reranking over time, learning them. And yeah, like just the key takeaway is that we should think of these different components, dense, sparse, fusion, and reranking, as a controllable lever. So something that changes depending on our application. And in this case, OMem provides this modular pipeline where you can turn things on and off to kind of test and see which configuration works best for you. Thank you very much. And I'm very happy to stay and answer any questions.